Today we'll be going over some essential concepts of superconductivity. This is a phenomenon in which there is an expulsion of magnetic fields and zero electrical resistance within certain materials called superconductors. This only happens after the material is cooled to under a certain critical temperature, which varies depending on the type of superconducting material. Let's say we place a superconducting block on a magnet at room temperature, and then we lower the temperature. Above the critical temperature, the block is not superconducting, and the magnetic fields will pass through it. Below the critical temperature, the block becomes superconducting, and the magnetic fields will be expelled from within it. This expulsion, causing the block to levitate, is known as the Meissner effect. A superconductor with no magnetic field within it is said to be in the Meissner state. This state breaks down when the applied magnetic field is too strong. Superconductors are divided into two types according to how this breakdown occurs. For type 1 superconductors, superconductivity is eliminated when the strength of the applied field rises above a critical value Hc. For type 2 superconductors, they behave as type 1 below the critical value Hc1. If the applied field is higher than Hc1, the superconductor is said to be in a mixed state known as the vortex state, in which an increasing amount of magnetic flux penetrates the material, but zero electrical resistance still remains as long as the current is not too large. At a second critical value of the magnetic field strength, Hc2, superconductivity is eliminated. Most pure elemental superconductors are type 1, while almost all impure and compound superconductors are type 2. Superconductors also hold the property of zero electrical resistance. The electrical resistance of a metal conductor decreases gradually as temperature is lowered. In regular conductors, such as copper, this decrease is limited by certain internal impurities. Even near absolute zero, such conductors still show some signs of resistance. However, for a superconductor, the resistance dramatically drops to zero once cooled below its critical temperature. Due to this, an electric current through a loop of superconducting wire can continue to exist indefinitely without a power source. This is what makes superconductors so special, and is why so much research is being done on bringing them into modern technology. One of the first large-scale applications of superconductivity is in medical diagnosis. Magnetic resonance imaging, or MRI, uses powerful superconducting magnets to produce large and uniform magnetic fields inside the patient's body. MRI scanners, which contain a liquid helium refrigeration system, detect how these magnetic fields are reflected by organs in the body. This ultimately produces an image that is, in fact, superior to X-ray technology for diagnosis. But why aren't superconductors in our everyday electronics? Well, materials are superconducting only when kept below their critical temperature. For modern-day practical superconductors, the temperature is much below 77 Kelvin, the temperature of liquid nitrogen. Keeping them below that temperature requires a lot of expensive cryogenic technology. Scientists are still working on designing superconductors that can operate at room temperature,